There is no shortage of mysteries in our universe, and among the most intriguing phenomena are black holes and their theoretical counterparts, white holes. Both have emerged from the general theory of relativity proposed by Albert Einstein and are opposites to each other in almost every way. While black holes are well documented and somewhat understood, white holes remain largely theoretical. Today, we're exploring key differences between white holes and black holes, two of the most extreme objects in our universe, and how they may be related. Black holes are simply one of the most awe-inspiring celestial objects in our universe. They form when a massive star collapses under its own gravity at the end of its life cycle, compressing its matter into an unimaginable dense point, known as a singularity. This singularity is a region of space that is infinitely small and has an infinite density. It's where the curvature of space-time becomes infinite and is surrounded by an event horizon, the point at which nothing, not even light, can escape. Theoretical physicist Stephen Hawking proposed that black holes emit a faint radiation due to quantum effects near the event horizon. This leads to the eventual evaporation of black holes over extremely long periods and is known as Hawking radiation. White holes, on the other hand, are purely theoretical objects and are proposed to exist as the opposite counterparts of black holes. While black holes pull everything in that comes near it, a white hole would theoretically do the opposite, expel all matter and energy. Nothing can escape a black hole, and nothing can enter a white hole. Once something leaves the event horizon of a white hole, it cannot return. Just like black holes, white holes are also thought to have singularities at their centers. But instead of attracting matter, the singularity at the core of a white hole would theoretically eject matter outward. Again, opposite to that of its black counterpart. White holes are thought to be highly unstable with very short lives due to their inherent contradiction with the second law of thermodynamics, which states that entropy in a closed system tends to increase. Because white holes would reduce entropy, they are believed to be unrealistic in our current understanding of our physical universe. Despite being opposites in function, black holes and white holes have several similarities. Both arise from solutions to Einstein's general theory of relativity, both have singularities at their center, and both have an event horizon. However, they exhibit dramatically different behaviors, which leads to several important distinctions. A big difference between black and white holes is in how they form. We understand that black holes form through the gravitational collapse of massive stars at the end of their life cycles. When a star runs out of nuclear fuel, its core will collapse under its own gravity, leading to the formation of a black hole. The formation of a white hole remains theoretical and open to speculation. They are a theoretical solution to Einstein's equations and have not been actually observed in the universe as of yet. Some theories suggest that white holes might be linked to black holes through wormholes, or that white holes could be born from the death of black holes, such as the final stage of Hawking radiation. But at this point, we can only theorize how and when a white hole forms. Until then, they are a mystery and remain but a theory. They remain theoretical constructs that are based on the mathematics of Einstein's theory of relativity. If white holes do exist, they could be extremely rare and live very short lives, making them difficult to detect given our current technology. The aspect of time also differentiates a black hole from a white hole. Inside a black hole, time and space are warped to such an extreme degree that time essentially freezes at the event horizon, at least from the perspective of an outside observer. Time inside a black hole may flow differently, contributing to the complexity to understanding the physics of a black hole, given our current understanding of our universe. In white holes, time theoretically plays out in reverse within the event horizon. This makes them conceptually difficult to reconcile with our understanding of thermodynamics and the arrow of time. This is where events in the universe naturally proceed toward increasing entropy. The laws of physics make even less sense with white holes and may require a new kind of understanding that we currently do not possess. One of the most intriguing things connecting black holes and white holes is the idea of a wormhole, or Einstein-Rosen bridge. This concept, which is rooted in general relativity, suggests that a black hole could be connected to a white hole by a tunnel through spacetime. This would allow matter to enter a black hole, travel through a wormhole, and emerge from a white hole in a different part of the universe, or even in a different universe altogether. But the problem is, wormholes are also highly speculative, and even if they exist, they would likely be highly unstable and collapse too quickly to be traversable. Still, the connection between black holes, white holes, and wormholes remains a fascinating topic for theoretical physics. The question of whether white holes even exist is an open topic for discussion. While black holes have been observed indirectly through various means, white holes remain 100% theoretical. The reason is in the second law of thermodynamics, which states that entropy, or disorder, in a closed system can never decrease. White holes would seemingly violate this law by reversing entropy, making them conflict with our current understanding of the laws that govern our universe. Some physicists have proposed that white holes could have existed in the early universe, potentially playing a role in the Big Bang or the formation of certain cosmological structures. Others speculate that white holes may appear in the far future, when black holes evaporate through Hawking radiation. What we do know is that black holes and white holes represent two extremes in our understanding of the universe. While black holes have been observed and studied extensively, white holes remain theoretical and only allow for open debate and speculation. As our technology and understanding of physics continue to advance, it may be possible that future discoveries may shed light on these enigmatic objects and the role they play in our universe. We thank you for watching and look forward to seeing you in our next episode,